Hi everybody, welcome to my second torsional bar video. In this video I'm going to talk about the similarities and differences between the area, the first moment of area, the second moment of area, torque, center of mass, center of area, and centroid. So you might have heard all these terms before and you probably have a good idea what they are, but since we're going to be using them a lot in both torsional bars and beams, it's very important to have a good understanding of what these actually mean. So, we all know what area is, right? And if you look it up, area is defined as the amount of space in a boundary. Alright, that's pretty straightforward. We can imagine we have a box. With dimensions b for base and h for height, and then of course the area is just going to be base times height. We give area the symbol A, and of course we know its units are meters squared. Alright, that's pretty straightforward. One thing to note about area is it's independent of position. So we can have the area of this box up here, we can have it down here, it's the same. We don't need to define an axis or something that we need to base this area off of. Alright, that's in quite a bit of contrast to first moment of area and second moment of area. Alright, so first, okay, so the definition of the first moment of area is this. I give it the symbol Q, it might be called something else, but I call it Q, is the sum or integral of y dA. Now in simple words, if we would take this y out and integrate dA, we would just get the area, right? So this is basically like a weighted area, and it's weighted by a factor of y to the first power. That's why it's called the first moment of area. So it's basically like a form of weighted area. And in this, we need to define an axis to base it off of. Because if we're timesing it by a distance, we need to have a point where we measure the distance from. So the moment of area of something is going to be different depending on where you define it to start from. So let's just take an example here. I'll define my axes to start here. And from there I'll let y get bigger as it goes up. And then I'll have something sitting on top. Alright, kind of like before, just a little bit different. So in order to find Q, or the first moment of area, we just need to use this equation and integrate. And this will give us the moment of area of this square about this axis here. Okay, so we just arbitrarily define that axis. If I were to define the axis to go through here, then we'd integrate from down here all the way to up here. In this case, we're going to integrate from here to here. Okay, and every time it'll give you a different answer. So let's quickly do this. Q for this piece, the integral is summing up all the y times area, right? Because it's not going to be the same. That's why it's an integral from y equals 0 up to y equals h. Y. Now what's dA? So we can imagine a tiny bit of area, dA. Alright, it's going to be like a bit like this. Small little section. So let's blow that up down here. Alright, so this is going to be the regular width, but we're only going to take a differential height. Okay, and then of course the area of this, dy, that's dy here, so that's going to be an amount dA. Alright, so we take this, plug it back into this equation here, b dy. Alright, you integrate this, you get y squared by 2, sub in the h, All right, we'll keep on going down here. We get Q equals BH squared by 2. Okay, so this is technically the right answer, but when you're doing this in questions, you don't want to work through this integration all the time. It's just a waste of time, and it's just only good for, defining what it is. So let's just redefine this in a way that's easy to find when you need to calculate Q. So notice we have a B times H squared. So this can be rewritten as BH times H by 2, and B times H, well, that's the area, all right? Just like we had here, same sort of shape. So that equals the area times H by 2. All right, now if you look carefully here, H by 2 is the distance to the centroid of this piece. All right, now the centroid, all right, this is another definition you kind of need to understand. The centroid is just the geometric center of an object, all right? So in this case, it's right smack dab center of the square. If you have a rectangle, the centroid is going to be a third of the distance here, all right, or 2/3 from that way. Okay, and for different shapes, it's different things, and there's a calculation you can do to find that. But you really only need to know it for a square or maybe a triangle in this course. Okay, now that's the centroid, and that's in stark contrast to a center of mass, because a center of mass can be not in the same position as a centroid, because if you remember, the centroid is geometrical. The center of mass has to do with the mass of the thing. So if this has a uniform mass, its centroid and its center of mass will be in the same spot. Okay, but if it's, say, the mass is like somehow increasing over here, the center of mass may be located further to the top, the centroid will still be down there. Okay, so keep that in mind. We're looking for the centroid of this thing. Usually it's the same thing as the center of mass. Alright, so moving along here, let's just redefine Q. It's a definition you should remember. Area times the distance to the centroid. Alright, and that's the one you want to use all the time, because it's just a simple way to remember it. And of course the units, area, that's meters squared, times distance, that's just meters, so the units are meters cubed. Notice how this is just one more power than it was up here. Alright, so area, first moment of area, we're increasing the power by 1. Okay, let's get into second moment of area. Okay, so the definition of this, I like to give it the symbol I. You can also call it the moment of inertia. Alright, that's another common, is the integral of y squared dA. Okay, that's why it's called second, because it's raised to a 1 higher power than the first moment of an area, which was 1 more higher power than A. Alright, now this is a very key in bending of beams, and in a lot more things, also in shear force in beams, but then in this case Q is also going to be in the shear force of beams. But I is a very important concept in engineering. It basically gives you how much resistance to twisting an object has. Like if you remember from your physics, you might have used moment of inertia. If you're spinning something, alright, it's kinetic energy, as a side note, it's half I, there comes your moment of inertia, omega squared, which was the rate of spinning. So the bigger the moment of inertia, the harder it is to spin, or when it's spinning, the more energy it has. Okay, so don't worry about this for now. Let's get into an example. So let's take the same piece and redefine it with our axes that we're going to take this y to be measured from. Let's take it to be exactly in the center. Alright, I could have chosen it to be off the bottom, off the top, somewhere here, a quarter down, but since it's very important in the later applications that we know the moment of inertia of a square relative to its centroid, I'm just going to derive that one here. So let's add some dimensions. Alright, so same dimensions as before. Just a height and a base. Okay, so the moment of inertia of this piece then is going to be defined as the integral of all these pieces. So from y equals, measured from this axis, well, we're going from negative h, alright, because y is measured like this, negative h by 2 up to positive h by 2. Right? And then y squared dA. Now by the same logic that we found dA over here, we can find dA here. It's just a thin strip of length b and of height dy. So it's going to be b dy. And then you can go through and integrate this. It's going to be, of course, y cubed b by 3, and evaluate it from y equals. Alright, now notice this here is to the power of 3. So we can simplify this function because we have, it's like a case of mathematical symmetry because it's to the power of an odd number. So now we can rewrite this as I is simply 2 times y to the 3b from y equals 0 to h by 2. Okay. Alright, let's keep going here. So we plug in our numbers and we get I equals to bh cubed by 12. Okay, and this is for this particular square relative to the center. Okay, so let's take a look at the units of this thing. So we have base, that's just meters, and then height cubed, so that's some meters to the power of 3, so total is meters to the 4. And we could have known that already based off of what we've seen here, knowing that this was meters cubed, and then the area, of course, was just meters. Alright, so we're measuring this relative to an axis, alright? But sometimes we want to know this relative to another axis, and there's a simple way of calculating that. Rather than setting up the whole thing and then going through and calculating it, because let's assume we had our axes here. And our object up there. We wanted to know the moment of inertia around this piece here. Okay, so basically how much would it spin around here? Assuming that the distance here to the centroid is called d. So what's the moment of inertia here? Well, instead of going through the whole integration, we use something called the parallel axes theorem. And that tells us that the moment of inertia of this piece is equal to the moment of inertia of itself about its centroid plus the distance away times the whole area of this thing. Alright, I'll go through what each one of these terms means again. So the moment of inertia about an axis that's not the centroidal axis is the sum of these two components. The first one being the moment of inertia of that thing about the centroid plus the distance away to the centroid, so I can actually call this dc, times the area. Alright, this is the parallel axis theorem, and this will give you the moment of inertia about this axis here. And we can check the units. This is meters to the 4, still from here. This is d squared, it's meters squared times area, that's still meters to the 4th. Alright, so that pretty well concludes what I have to say about these things. So just in a quick review, the area, alright, I think we all know what that is, the amount of space in a boundary. Alright, area is b times h, and this is independent of where it is on the map. Alright, you can have an area in the North Pole, area in the South Pole, measured relative to the equator, doesn't make a difference. Q is defined as the area times a distance to the area, and we need to usually find this by integration. Alright, and I work through a simple example to find the moment of area of this thing about an axis on the bottom, and we found it to be, after we work through it, the area of that piece times the distance